Now note here, ladies and gentlemen, that we can kind of now take a look at the three different triangles that we have here and see what they have in common and what's different. They all have 54-degree angles, which makes sense here because we're told one of the angles is 54. But this triangle down here, as you can see, is a lot different from these other two. In particular, we look at their largest angles here. We have a 99 here and a 108 here, and here we don't have that. Here we have a 84 is our largest angle here. So notice how in this situation here, we have two triangles that look to be sort of like slanted to the left like this, whereas this one doesn't look that way. So we can actually identify the triangles based on their angles here. So in this case, we can take a look at something like this. So for instance, this smaller triangle, the triangle in case 3 here, we see that all these angles here are less than 90 degrees. So we can define this idea of a triangle, we call it acute. So we can classify triangles based on their angles here. So we can say that a triangle is acute if and only if all of its interior angles are acute. Notice that in this situation, we want to mention here, we have to say all of them are acute, right? Because otherwise, our definition is not going to be wholly complete here, right? So we want to keep that in mind. Of course, with acute triangles, we can also have the obtuse triangle, which is what we had over here, right? In this situation where we have these two things here, we can have the obtuse triangle like so, right? Where the largest angle is obtuse. And we could also have our right triangles here. So note that we can define in this situation our triangle. So triangle is right if and only if it contains a right angle. And a triangle is obtuse if and only if it contains one obtuse angle here. So we note that in this situation, we can also talk about this idea of triangle classifications like this here. So all of our triangles will fall into exactly one of these three categories. The nice part about this is that these three categories are mutually exclusive. You can't have a triangle that fits into multiple of these categories at the same time because it's just not going to be possible. All these are based on the size of the angles here. And in this situation here, right, in this situation, the largest angle is a right angle, the largest angle is an obtuse triangle. Here, the largest angle is an acute angle here, okay? Because if the largest angle wasn't an acute angle, then it would not fall into this category here. Now, of course, there are some other categories that some of you might know of here, right? If you go back at the triangles here, we notice that in a situation like this, in every single one of these triangles, none of the angles match. All the angles are different here. So here we see 27, 54, 99, same thing here, none of the angles match. So we can refer to that. We can also use a different set of categories to determine triangles here. Now, these categories, unlike these classifications up here, these categories can overlap a little bit. In particular, we can talk about this idea of scalene. So we can say a triangle is scalene if and only if it has no congruent sides or no congruent angles. You'll note that these are actually interrelated. If a triangle has no congruent sides, then it must have no congruent angles and vice versa. But that's a story for another day. We'll prove that eventually. So notice that we can talk about this idea of scalene here, of course. Now, in addition to that, we also have this idea of what are known as isosceles triangles. And we talk about this idea of an isosceles triangle if and only if it has two congruent sides or two congruent angles here, right? So let me just quickly run through this here, and I'll get back to the definition here in a bit. So with the isosceles triangle, I think you're all pretty familiar here, right? Our isosceles triangle often looks something like this here, okay? So here is our isosceles triangle. So let's say, we can identify an isosceles triangle by looking at two congruent angles here. So let's say this is 70 and 70 down here, right? So the top angle should be, I believe, about 40, okay? So notice how in this situation here, we kind of set this up like so. We note that these here, the two angles here that are congruent, these are known as the base angles here. These are the congruent angles. And we mentioned that congruent angles, we call them the base angles, even if the triangle is sort of lying on its side or upside down. I can still have these be base angles, even if the triangle is upside down like this here. So the two congruent angles are the base angles here. And the last remaining angle on top here, we refer to this, as our vertex angle. Okay? So notice that in the isosceles triangle, we actually have names for this here. And notice that with the isosceles triangle, we also have congruent sides. Not only do we have congruent angles, we also have congruent sides here. So in this case, it looks like because these two angles are congruent, it looks like the blue sides, the sides opposite them, are also congruent as well. So in this case here, AC and AB are congruent here. So notice the more important thing about this is that we have this sort of opposite business here. Okay? And we refer to these two congruent sides here. These are the legs here. So there's a leg and there's a leg here. Okay, so we refer to these as the legs of the triangle. So what appears to be true for isosceles triangles is that congruent legs lie opposite the congruent base angles. And this also works vice versa. It seems like it can go backwards as well, that congruent base angles will always lie opposite the congruent legs. Now, why is this true? Well, for now, let's take this on faith, because we will eventually prove this to be true. But right now, we kind of don't have the equipment to prove this true. It's kind of like, we're going through a video game and we have this giant boss in our way here. We are way too under-leveled. If we try to go in right now, it will absolutely thrash us. We need more gear. We need to level grind a little bit. So we're going to do a little bit more proof theory here, and then eventually we're going to come back and tackle this. So we'll come back to that, I promise you that. But for now, you can take this as truth, right? You can say that for an isosceles triangle, this is going to be a true statement here. So again, note that we talked about this idea of isosceles triangles. In addition, we also have this idea of an equilateral triangle here, where instead of having two sides being congruent, all three sides are congruent. And one of the things, note that this definition for isosceles says at least two. So this means that the equilateral triangles are also isosceles triangles. They just happen to be a specific type of isosceles triangles here. So again, if and only if all its sides are congruent. And of course, we also have this idea of equiangular triangles, if and only if all its angles are congruent. So in this situation here, because we exist in Euclidean geometry, it turns out that these two things are synonymous. If a triangle is equilateral, it must be equiangular, and vice versa here. Again, that's something, let's take that on faith for the time being. We will show that it's going to be true later on. Again, we don't have the tools to prove it yet. Once we're able to prove the isosceles triangle bit, we can do this here. So notice that if you have an equilateral triangle, it must also be equiangular, and vice versa here. There are different kinds of geometries out there where there are situations where triangles will be equilateral but not necessarily equiangular, and vice versa. Triangles that are equiangular but not necessarily equilateral here. But that's something far, far beyond what we're meant to do here. And we're actually going to use these terms later on when we talk about things other than triangles.